Hey guys, this is the beginning of chapter 5, and we're going to be talking about circular motion and gravity. And eventually we'll get into the gravitation and what that affects, how that has to do with planetary motion, satellites, things along those lines. We know gravity, we understand a little bit about gravity here on the Earth, on the surface of the Earth, as a person who's fallen down or thrown an object through the air. We get a basic idea of how gravity works. You know, we think of it as making things come back to the Earth or fall. But it's about much more than that. And so we really want to understand that. And so we're going to have to understand some things about circular motion in general that are going to help us understand why Newton's law of gravitation, universal gravitation, makes sense and why it is the way it is. So as we kind of get started, we need to understand a couple of things about the kinematics of uniform circular motion. We are going to assume that an acceleration means a change in velocity. And since velocity has both a magnitude or size, or in other words the speed, and it has direction, anytime we're talking about an object that's moving around a circle, okay, as it's going around the circle, that means that we have to acknowledge that there's some sort of acceleration. But what direction is it accelerating? You know, what is the speed changing? The answer is no, but the direction does. And so we need to recognize how that affects the motion of the ball and how we can make predictions about that motion. We have a couple of different names you'll see listed to reference it. When we talk about this acceleration that is pulling inward, okay, you can see it over here on the right. As the object wants to go in a straight line, there has to be a pull towards the middle of the circle in order to force it to turn its behavior. And so we're talking about this curve being created by some sort of acceleration that's in along the radius. Okay, that is to say, let me grab my marker here real quick. That is to say that for any circular motion, okay, if this is the object, the acceleration that we call it radial acceleration, or AR, it's also sometimes referred to as centripetal acceleration. So centripetal acceleration is something that it's a pulling towards the center, okay? So center pointing or centripetal. It's also sometimes called radial because it's along the radius of the circle. In the text, we're going to use AR a lot. That's just because it's along the radius. But the centripetal acceleration or the radial acceleration is something that we need to understand and be able to make some predictions about. It turns out, by some simple calculations, that it depends on the radius of the circle. And the bigger the radius, the less acceleration we have to feel. I want you to think about this for a second. If you've ever been on a merry-go-round before, or maybe been on a marching band, things along those lines, gone roller skating and you're doing a little whip type deal where you spin in a circle with a bunch of people, the further out you are, the less you feel that you're being pulled. It doesn't take as much to turn you because your curve is almost flat. If you think about it, a big circle, the curve is barely turning, whereas on a small circle, you're going through a lot of degrees of rotation really rapidly, right? Boom, boom. So as we go through that really rapidly, we recognize the smaller the radius, we're going to see a big force or big acceleration to do that. And we're going to experience that, okay? So this is our formula that we're going to use for the acceleration in the radial direction if we're to maintain a uniform circle. Okay, so a couple things. One, we don't want the velocity to change. We're trying to keep the same speed. Let me rephrase that. We want the same speed. And so if we're going 2 meters a second, we want to stay 2 meters a second. But the direction's going to change along the radius. It turns out that the centripetal acceleration is equal to the velocity squared divided by the radius. That allows us to do a lot of things and a lot of calculations. If we keep going, we can find a couple of other things, and these are not near as important. We're going to kind of skip over that. I think that's fairly conceptual. Now, you have to understand a few things that come out of that. In order to get something to stay in a uniform circle, meaning it's going to stay at the same velocity the whole time, then I have to be pulling inward, always to the middle, with a very specific force, because I need a specific acceleration, okay? And Newton's laws tell us that force equals mass times acceleration. If I want to have it follow a perfect circle, then the force has to be a very specific set value. And so we see this written this way. The forces in the radial direction, or the sum of those forces, when you add up all the forces, has to equal the mass times our centripetal acceleration, or more commonly, mv squared over r. Often in class, I'm going to write it like this. Just one big fraction, mv squared over r. This is the amount of force I have to be pulling in with. Now what's really interesting is, in different parts of the circle, okay, that force has to be coming in here. As it's moving, that force now has to be pulling from the other direction. So if you think about spinning something in a circle, you've got to have your hand always pulling against that string, always towards the middle as it comes around. Now if you're spinning something in a vertical circle, some really cool things happen. You actually end up with, gravity can help you out. If you think about a ball on a string, I'm pulling in with a certain amount of force. That force, okay, has to balance to give me the mv squared over r. But if gravity is helping, right, so if gravity is also pointing down, then I have to lighten up my force. I can't push as hard. I gotta make it a little smaller, or else I'm going to end up pulling down too hard and the circle is going to cave in. Same sort of thing happens down here at the bottom. When I'm pulling up, I need my centripetal force to overcome gravity, which is pushing down. So now I'm going to have a much larger pull towards the middle in order to get the mv squared over r to stay constant. So the concept of just spinning something in a circle, it's actually way more complicated than you might think, because we have to constantly be calculating and thinking about these things, in the subconscious, in the back of our minds. But we want that velocity to be constant. We're going to have to make sure that the force is also constant, or that the net force, let me restate that, the net force or total force is constant. All right, let's take a look at, let's see, going around a banked curve, going around highway curves and having them be banked, okay? This is actually going to be related to one of your bonus questions. I'm happy with you just digging some information out. These are actually a little bit more challenging than you think. But if you look at this, okay, we think as you go around a corner, everybody wants to go straight, but we're going to pull inward in order to get the car to turn. Well, what exactly is causing it to turn? There's only one force that's acting on the car in this sideways direction, and that is the force of friction on the tires. So what that means is that if I drive around a corner, just a straight flat corner, the force of friction would have to equal my centripetal force, which would be mv squared over r. So when I think about the force of friction, which we know is mu mg cosine of theta, all right, and theta, if this is flat and horizontal, would be 0, and so it would just be mu mg. It would have to equal mv squared over r. So we could make some pretty cool calculations here about how fast I have to go around the corner, or what the radius has to be. And so right here, we're able to actually make a lot of calculations about velocity and radius. So this tells a surveyor or a civil engineer how big of a turn we need to take in order to prevent the car from sliding off the road. Now the truth is, that can make us have to take a pretty wide turn. If we make that radius big enough, then we don't have to worry about so much force. The problem is we don't always have that much space, and so we have to have some other way of getting more friction or getting more centripetal force from the nature that we're dealing with than what we might get on a traditional corner. And so what we're going to do is we're going to notice that if we get this done just right and we bank the angle of the road, okay, we're actually able to get a lot more out of it. Now, a couple things. This is going to mess us up a couple of ways. So when we bank that turn, what we're going to be able to do, okay, we're going to have part, not all, but part of the normal force is actually going to be deflected in the direction of the center or the radius. That's really important. We're not going to deflect along the surface. This is going to change our XY axis. I know on a slanted curve we always wanted to do it a certain way. Here we're actually going to have to tilt that back to a traditional XY, because our inner direction is not along the slope, it's just in horizontally. So what that means is we have that information, and there's a little bit of friction too, the force of friction, okay, which we would have to deflect the force of friction from being down and in to just this piece, okay? And so what that means is that, you know, we would want some friction to help us out, and we would use, you know, whatever our let's see, we'd be on the opposite side, or the adjacent side, so that'd be a cosine, okay? And so we can go through and we can calculate that. Now, that being said, we're going to pause for a second. This first question, and one of the most important questions, is what if it's completely icy and I can't predict that there's going to be any friction? What if I don't want someone to ever slide off this road? Well, that's where this comes in. What if we only used the normal force, the part of the normal force pushing to the right, okay? And that had to equal mu times v squared over r. This is what we call, you know, it says right here, it's called the design speed. What that means is if all else fails and friction disappears for a moment, we want to be able to make sure this car can absolutely turn at a specific speed. And so we're going to throw information into that, and using that we can calculate what amount of speed, or what kind of bank we need in order to maintain a certain speed as we go around the turn. So that's kind of the idea there, is we want to be able to come up with the best case scenario. Non-uniform circular motion is something we're really not going to cover here in this class. Has tangential acceleration, meaning I'm also pulling to the side. It's going to speed up as it goes around the circle, or slow down. That's going to change some things. A centrifuge is something that you've probably heard of before. We use them to separate blood, separate atomic elements. If you want to use uranium, whether it's weapons grade or you want to use uranium for power, electrical production, you're going to have to separate uranium or other elements into different heavy and light versions. And we can use centripetal or centrifugal centrifuges to pull those larger masses. Will want to stay to the outside and carry in a straight line, whereas lighter fluids will be shoved towards the middle. And then that's kind of where we're going to stop. Hopefully that gives you a baseline of what we're talking about in class and helps you understand this idea of circular motion. We're going to definitely have to talk about it more, but good luck, and we'll see you in class.